Hi everyone. Today let's take a look at the end behaviors of functions. Here's today's FLT. Given a function, I will be able to identify the end behaviors of the graph using limit notation. So limit notation might be a new concept for you, but don't worry, we'll be going over that as well. So before we get started with end behavior, let's just take a quick look at how we label far directions. So say we have this empty graph with the x-axis and the y-axis. If you go towards the far left, you're going towards the direction of negative infinity. You can't ever really reach negative infinity, but you can head towards that direction if you're moving to the far left. And then if you move to the far right, you're approaching positive infinity. So on the x-axis, you're either moving to the far left or the far right. On the y-axis, if you keep going down, eventually you're heading towards the direction of negative infinity. And if you keep going up, you're going in the direction of positive infinity. Notice that for both axes, we use negative and positive infinity, but for the x-axis, we're talking about going to the far left or the far right, and for the y-axis, we're talking about going far up or far down. So now that we got that out of the way, let's start looking at end behaviors of functions. So end behavior just tells us how the graph behaves at its ends. Notice that ends is plural because you can go to the far left end or the far right end. And to show end behavior, we're going to be using limit notation. So please copy this carefully. I have lim, and then x, and then an arrow to infinity, and then f of x equals some kind of number. Right here, I wrote the lim and all the little x arrow infinity stuff a little smaller compared to the f of x. So formatting is really important here. And let's go over how to read this limit notation, because right now it just looks like a bunch of letters and symbols. So we read it like the following. The limit of f of x, that's our function, as x approaches infinity is, and then whatever number it is. And let me try to color code each part so you see which part corresponds to the parts in the notation. So here's the limit, and then we have the function f of x, and then x approaches infinity is denoted by the x and then the arrow infinity, and then there's the number, this part. So try reading this out loud to familiarize yourself. The limit of f of x as x approaches infinity is some kind of number. And a simpler way of saying this would be like, what's the y value as x approaches a certain direction? So in this case, what's the y value as x goes towards positive infinity? So as we go to the far right. And so this y value would be our end behavior for going to the far right. We also have the option when x goes to negative infinity. So right here, x and then the arrow to negative infinity. So how would we read this notation? The limit of f of x as x approaches, and now we're going to the far left. So as x approaches negative infinity is some kind of number. So a simpler way to ask this is, what's the y value or the end behavior when x goes to the far left, negative infinity? And here I'm just color coding real quick. And right now, this new notation might still look confusing for you, but hopefully as we walk through examples, it'll start to make more sense. So for our first example, we're going to find the end behavior of y equals x. We're going to start off by providing a graph or a sketch of this function y equals x. Notice that this is a linear function, so the graph is going to be a line. So I draw my axes first, and then I draw this line going through the origin, and these arrows show that this line keeps going forever and ever in each direction. Okay, so let me write the limit notation in the order that I say it. So the limit of f of x, or y, same thing, as x approaches infinity equals, and we got to find out what our y value is as we go to the far right. So as we move towards positive infinity. So this Mario is just going to go to the far right. It's going to keep going right. And see how it goes on and on and on. It keeps going up. We're going in the direction of going far up, which means we're approaching positive infinity. So make sure you're distinguishing these infinities. X approaches infinity talks about going far right, whereas this limit, the end behavior, talks about going far up. And then we have to look at the other end. So what is the limit of f of x as x approaches negative infinity? So what's the y value as x goes to the far left? So what happens as Mario starts going to the far left? He's going more and more down. So he's approaching negative infinity. So the limit of this function as x approaches negative infinity is negative infinity because we're moving far down. So the more left we go, the more down we're going. So this x approaching negative infinity talks about going to the far left, whereas the equals negative infinity talks about going far down. So let me read it aloud one more time. The limit of the function as x approaches positive infinity is positive infinity, and the limit of the function as x approaches negative infinity is negative infinity. Sketching the graph helps us see the end behavior visually, like how we saw in this line. The more right you go, the more up you go, and then if you keep going to the left, eventually you hit negative infinity because you're going down. For our second example, let's find the end behavior of y equals x squared. So this is just your average parent function parabola. So go ahead and try sketching it on your own. So hopefully your sketch looks something like this, where you have a parabola and the arrows show that you keep going on and on and on. Okay, so let's find the end behavior. So first, what's the limit of this function as x approaches positive infinity? What happens as we move to the right on this function? We would keep going and we'd keep going up this curve. So we'd be approaching positive infinity. And then let me erase this highlighter thing. Okay, we gotta find the behavior of the other end. So what's the limit of this function as x approaches negative infinity? So what happens as we keep going to the left? So if we traced our finger on the graph and kept going to the left, we'd also approach positive infinity because we keep moving up. In this case, both ends of the graph approach positive infinity. On Edpuzzle, please find the end behavior of y equals negative absolute value of x. I provided a sketch, so look at what happens as you go to the far right and what happens as you go to the far left. Sometimes you might get a graph that looks a little wonky like this. Try your best to copy this sketch down into your notebook. And let's find the end behavior of this function. So first, what happens as we go to the far right? So what's the limit of f of x as x approaches infinity? Well, here, as we go more and more right, we're going in the direction of negative infinity. We're going far down. And let's take a look at the other end as well. This is where it gets a little trickier. So what's the limit of this function, f of x, as x approaches negative infinity? So as we go more and more left, we get really close to the x-axis, but we never actually touch the x-axis. We're just approaching it. So what's the y value for the x-axis? If you're approaching the x-axis, it means you're approaching y equals 0. So the limit as we go to the far left is 0. We never actually touch 0, but we're getting really close to it. So in this problem, as we move to the far right, we were going in the direction of negative infinity, but as we move to the far left, we were approaching an actual number, 0. Please try this similar example on Edpuzzle. Find the end behavior of this function. Notice as we go to the far right, we're approaching the x-axis. What does that mean? Okay, so one of the goals for this unit is for you to be able to sketch higher order polynomials. So stuff with higher degrees like x to the power of 7 or x to the power of 6. So today, let's compare the end behaviors of odd degree functions and even degree functions. Odd degree functions are stuff like y equals x, or y equals x cubed, y equals 5x to the 7th power. And then even degree functions are functions like y equals x squared, or y equals 6x to the 4th power. Before we compare the odd degree and even degree functions, let's take a look at the word leading coefficients. The leading coefficient is the coefficient of a polynomial's leading term. So think of it as the term being in the lead, so the term with the highest degree. So we're looking at the coefficient of that term. So again, the leading term is the term with the highest degree. So for example, if I had y equals 7x cubed minus 5x plus 9, my leading coefficient is 7 because it's the coefficient of the polynomial's leading term, the term with the highest degree. And if I had this function, y equals negative 4x to the 6th power plus 2x minus 1, what's my leading coefficient here? It would be negative 4. So keep this idea in mind as we start making comparisons between different types of functions. So we're going to be comparing the end behaviors of odd degree functions versus even degree functions. And I'm going to use Desmos to show you guys a few examples so that you can make some observations of each type of function. Let's take a look at odd degree functions first. So here I'm just typing in a bunch of random odd degree functions and focus on the n degree of these functions. Even though all these functions look alike, what do you notice about their n behaviors? Pause the video if necessary to think about the n behaviors. Did you notice that the limit of the function as x approaches infinity, so as we go to the far right, is positive infinity because we keep going up, and the limit of the function, any of these functions, as x approaches negative infinity, so as x goes to the far left, is negative infinity because we keep going down. So odd degree functions have different end behavior on each end. So as we went to the far right, the graphs approach positive infinity, but as we go to the far left, the graph approaches negative infinity. So they have different end behaviors at each end. And this was regardless of the exact functions. They all looked different, but they shared the same end behavior because they were all odd degree functions. And for those examples, all of the leading coefficients were positive. So we can make this observation as well. If the leading coefficient of an odd degree function is positive, then as x approaches infinity, f of x, the y value, also approaches infinity. And as x approaches negative infinity, f of x, so the y value, was approaching negative infinity. But what happens when the leading coefficient is negative? So here, I'm going to make all of the leading coefficients negative, and then take a look at how the end behavior changes. Now, the limit of f of x as x approaches infinity is negative infinity. So as we go to the far right, we're going more down. And the limit of f of x as x approaches negative infinity is now positive infinity. So when we go to the far left, we go more up. So it's kind of flipped around compared to when our leading coefficient was positive. So let's write this in our little chart right here. If the leading coefficient is negative, then as x approaches infinity, so as we go to the far right, f of x approaches negative infinity, we keep going down. And as x approaches negative infinity, so as we go to the far left, f of x, our y value, approaches positive infinity. We keep going up. But regardless of whether the leading coefficient is positive or negative, odd degree functions have different end behaviors on each end. So now let's take a look at even degree functions. I'm going to type a bunch of even degree functions here. And again, each graph will look different, but focus on the end behaviors. So what do you notice about the end behaviors? And I was just choosing random numbers at this point. But yeah, what do you notice about the end behaviors? Do you see that as we go more to the right, the graph approaches positive infinity? But also, even when we go to the far left, the graph is also approaching positive infinity. So even degree functions share the same end behavior on both ends. So regardless of whether we move to the far right or the far left, they share the same end behavior. In the examples we just looked at, our leading coefficient was positive. And what did we notice here? Well, as x approached infinity, so as we went to the far right, f of x, our y value, approached positive infinity. So as we moved to the right, we also kept moving up. And then as x approached negative infinity, so as we went to the far left, the graph was still approaching positive infinity. No matter whether we were going far left or far right, they shared the same end behavior. What do you think happens when the leading coefficient is negative? So I'm just going to turn all the leading coefficients into negatives. Notice they're all reflecting across the x-axis. Wow, math vocab, reflections. And now, notice that as we move to the far right, the function, the y value, approaches negative infinity because we keep going down. And also, as we go to the far left, f of x approaches negative infinity because it keeps going down. So when the leading coefficient of an even degree function is negative, then as x approaches positive infinity, so as we move to the far right, the function, or the y value, approaches negative infinity. It keeps going down. And same thing even if we move to the far left, the y value, or the function, approaches negative infinity because we keep moving down. I know there's a lot of information right here, so go ahead, pause the video once, play around on Desmos if you would like, and walk through each part again in your head. So what are the differences of end behaviors between odd degree functions and even degree functions? Okay, and with that in mind, let's move on to some examples. For our first example here, let's find the end behavior of this function. Y equals 4x to the power of 10 plus 7x cubed minus 2x squared plus pi. There's a lot of stuff going on in this function, but we're just focusing on the leading term. I want to see whether it's an odd or even degree function, and I also want to see if the leading coefficient is positive or negative. The highest degree here is 10, and 10 is an even number, so we have an even degree function. So that means they're going to share the same end behavior, regardless of which end. And then the leading coefficient is 4, which is a positive number. So we have an even degree function where the leading coefficient is positive. And at first, it might be difficult thinking back to that chart because there was a lot of information. But when in doubt, think about the simplest type of even degree function we've been looking at, which is y equals x squared. And this you know how to sketch, so let's do that. Just a parabola with these ends. Now, the function in this example would look nothing like y equals x squared, but since they're both even degree functions, they're going to share the same end behavior. So here, what happens at the ends, the limit of the function as x approaches infinity is positive infinity, because as we go to the far right, we keep going up. And the limit, oops, I wrote it in the wrong order, of f of x as x approaches negative infinity. So what happens when we keep going to the left? We keep going up, so we're approaching positive infinity. And this is because even degree functions have the same end behavior on both ends. And also, since the leading coefficient is positive, whether we go to the far right or the far left, we keep going up, so we approach positive infinity. And when in doubt, like I just did, you can just go back to the most basic type of even degree function we're used to and provide that sketch, because we know they'll share the same end behavior. All right, let's find the end behavior of this crazy function. Y equals negative 2x to the power of 7 plus 3x to the power of 4 plus 2x plus 5. Again, we only need to focus on the leading term, so the negative 2x to the power of 7. Is this an odd degree function or an even degree function? And is our leading coefficient positive or negative? The highest degree here is 7, which is an odd number, so I have an odd degree function. I'm going to have different end behavior on each end. And then my leading coefficient is negative 2. So what does a negative leading coefficient imply? I'm going to think of the most basic type of odd degree function that we're familiar with, which would be y equals x, a linear function. But then I notice here the leading coefficient is negative, so I'm going to use y equals negative x, and I'm going to sketch that to look at the end behavior. So I'm going to provide a sketch of y equals negative x, because even though the functions will look very different, they still have the same end behavior characteristics. So like the sketch shows, we're going in opposite directions here. So let's go to the far right first. So the limit of f of x as x approaches infinity is negative infinity, because we keep going down. And then what happens when we go to the far left? So the limit of this function as x approaches negative infinity as we go to the far left is positive infinity because we keep going up. So here we had opposite end behaviors because we have an odd degree function. And notice how the leading coefficient being negative also affected the end behavior. This is your last example on Edpuzzle. Please find the end behavior of this function. Okay, let's read this. Y equals negative 8x to the power of 6 plus 7x to the power of 5 plus 3x cubed plus 74. Even though there's a lot going on in this function, just think about the leading term. Is it an odd degree function or an even degree function? And also, is the leading coefficient positive or negative? Just as a review, the end behaviors tell you how the graph of a function behaves at each end in the directions of negative infinity, so far left, and positive infinity, going to the far right. Odd degree functions will have different end behaviors, whereas even degree functions will have the same end behavior. And refer back to that chart whenever you're doing practice problems. Great work today, and see you guys next time.